welcome students. Let's have another lesson this week. We are talking about area under the curve. And so we'll see how that connects to what we talked about last week and how it's going to move us forward in our understanding about data and statistics. If you're looking at the IM materials that we have, this would be lesson 6. So if you'd like to go there and download some of the actual lesson papers that we have, you can follow along there. And get some other practice and ideas and practice problems. But we're really going to just focus here on some data sets and some information we have here. So last week, we looked at the normal distribution curve, this nice bell curve that we have, that we can usually put most data into. Things like people's heights, their IQs, their salaries, really so much can be described using our normal distribution curve. It has our mean right in the middle, our average, and then we have these different segments off to the side that tell us what is kind of a little bit of normal variance. And so we call that standard deviation. What is normal to be a little bit of wiggle room around that mean, both going positive and negative. And so we started learning about how this can start showing us some probability of some values that we have. And so today we're going to talk about 2 different ways that we're going to calculate area under the curve. And these 2 ways, if you're taking some notes, which I recommend as you're watching this video, the first way that we're going to look at is to actually calculate area of the bar that represents it. So if we're looking at a certain segment and we'll see a data set that has a bar graph that's created or a histogram, and how we can calculate the bar area that's going to tell us the area under the curve. The other way that we're going to do it is something called the empirical rule, where we're going to use the distribution curve that we have here with mean and standard deviation to give us just kind of a rough estimate. So that empirical rule is pretty important. So let's get started with our first method that we're going to calculate based on the bar area of a histogram. So I have this data set on a Post-it note, and there's 20 total pieces of data here. And if we were to put this into context, I was thinking that these would be the ages of kids at a birthday party. And so I can see how many number 8s there are. This is probably an 8-year-old's birthday party, but not everybody at that birthday party has already turned 8. So there's some 7-year-olds, a couple 9-year-olds, maybe a 12-year-old, maybe somebody brought their younger sibling, and so there's a 4-year-old there too. And so I took this data set and I made it into this histogram to start keeping track of how this data starts to be distributed. And as you can see, it's pretty close to a normal distribution curve. We have a nice spike in the middle, which makes sense because there's going to most likely be a lot of 7, 8, and 9-year-olds at an 8-year-old's birthday party. And then it kind of tapers off as we go to the sides. So this 8-year-old, we have, as I look off to the side, we have a total of 6 people who are age 8 at this birthday party. And so we have lots of other different ages as well. So if I'm trying to find the area under this curve that we can draw, I can really look at each of these as a rectangle bar graph. And if I can calculate the area of the bar and compare that to the area of all the items underneath the curve, I can also find some percentages and see what the likelihood is of some of these different things happening. So our first way that we could do it, let's say that I want to find the area of age 8. When I'm looking at the area of a rectangle, I just need length, or height, I should say, times width. So how wide is it? Times the height. And if I look at the bar for the 8-year-old, it is 1 unit wide. Everybody in this bar is age 8, so it only has 1 age in this bar. So our width is 1. And when I look at our height, I see that our height is 6. So the area of this bar would be 1 times 6, or just 6 units. And I can do this again for lots of different ages that we have in here, right? So the bar for the 6-year-old age, again, it only has 1 wide and 2 high. And so if I calculate the area of every single one of these bars, I'm actually going to find that our total area is 20, right? And that makes sense because each age we separated by 1 year and we had 20 data points. And so now I can start to take the area of the certain bars that I've found over our total area under the curve. In this case, 20 units, right? 20 data sets, or each of these multiplied out, this would be obviously 1 unit and another 1 unit. This is 1 times 2. This is 1 times 4. 1 times 6. 1 times 3. 1 times 2, and 1 times 1. When I add all of these areas together, I get a total area of 20 units. So to find our probability of, say, an 8-year-old happening, it would be the 6 units of that bar over the 20 units of the total area under the curve. And then I could calculate what is the probability of randomly choosing an 8-year-old from all the people, or what the makeup is. This is 30% of the kids at this party are 8 years old. So I did that by doing 20 units, the area of our bar, divided by our total number, our total units of area. So 0.3 or 30% of our people at this birthday party are 8 years old. Now we bring up this idea of height times width because we can also change the scale and we can use lots of different ways of going about this, right? So I'm going to delete what I have. I'm going to keep my same data set, but we can also put these into some different categories. So perhaps I'm not interested in their individual ages, but I want to put them in age ranges. So maybe I want to have a range of 4 to 5-year-olds, 6 to 7, 8 to 9, 10 to 11, and 12 to 13-year-olds. Each of these bars has to represent an equal amount of data, right? So each of them is a 2-year span. So notice now our width of each bar is going to be 2 units because we're including both ages. And now if I use my same data set and just create a histogram, I have a 12-year-old, another 8-year-old, a 4-year-old, a 7, 8, 9, 10, 9, 8, 7, a 6-year-old, an 8-year-old, a 6-year-old, a 9-year-old. I'm going to fall off the board. Uh-oh. A 5-year-old, a 7-year-old, and a 10-year-old. Okay. So now what I have, again, it's still a fairly evenly shaped curve that I could draw over all of this data. And I can start to calculate again the area under the curve. So this time, what I'm looking at, if I draw this rectangle up here for my 8 to 9-year-olds, I have a rectangle that has a width of 2, right? It has 2 ages in there now, so it has a width of 2. And when I think about the height, how many it represents, 1, 2, 3, 4, 5, 6, 7, 8, 9. This one has an area under the curve of 2 times 9, or 18 units. And we can keep on finding that again for lots of different values and different bars on this graph. If I look at the 10 to 11-year-olds, I see it's 2 units wide times 2 units tall. This one has an area of 4 units. 2 times 2 area is 4. Our bar here is 1 times 2, an area of 2. And so again, if I keep on totaling up all of the different bar areas, I can find the total area under the curve. 6, this one's 12. Over here we've got 2 times 2. And so now, when I'm looking at what our total area is, I have 20, 30, 40 total units. All right, so notice that this one has a total unit here of all of our bars together. Our total area of all of our bars is 40 units. All right, so notice that that's our number of data points that we had here, times each number of bars. Each bar represents 2 ages, and so that's our total number of data points times 2, because each bar is worth 2. And again, I can still calculate the percentage of a certain age group happening. So if I'm looking at my 6 to 7-year-olds, it's 12 units is that area, 40 units total. And when I do 12 divided by 40, let me push all the right buttons here, we're again at randomly, magically, a 30%. So 30% of these kids are age 6 or 7. Okay. So one way that we can find the area under the curve is to calculate the value of the distance here, the length at the bottom, times our number of data sets in there. Okay. Now there are lots of ways we can represent that. And I just want you to be familiar with the fact that even something that is written as a histogram like this is an example that they have in our workbook, and it's measuring how many different boards. We're at a lumber yard here, and so they're looking about how long each of their boards are and tracking how many. So they have 5,000 boards that are happening, and they put them into half-foot categories here. So board length, so if it's anywhere from 5.5 feet to 6 feet, it's going to count in here. All right, and so we can see this nice normal curve going on here based on how much it is. And to find our area of any one of these, we would be looking at, let's start with our total area first underneath. If we have 5,000 boards, right, this is how many data points we have. And we multiply it by how wide each bar represents. In this case, each bar represents a half a foot. So 0.5 going on here. If each bar is half a foot, we could find the total area under the curve. I know that our total bars are all going to add up to 2,500 units. So that's our total area under the curve, our number of data points times how wide each segment is that we're separating them into. And now to find what each one could be, right? If I look at this bar here from 6.5 to 7, 6.5 to 7 tells me it has a height of 753. So if I were to follow this over to the side, I'd be at about 753 boards at that height. So if I have a height of 753 and a width of this rectangle at 0.5, the area of this bar, 753 times 0.5, has an area of about 376.5 units. And so again, I can find out what that total amount is, 376.5 units, divided by the total number of units that we have under the bar graph, under the graph here. We're looking at about 15% of the boards, or 0.1506 probability. that if we picked a board at random, we would have one that's between 6.5 to 7 feet. Okay. Now, we can also do this for multiple boards. So I just want to let you know also, we're looking at the possibility of saying, well, what if we're looking at the total between 5 and 6 feet? We would just calculate each rectangle's area separately, add them together, and take that total of the 2 bars divided by our total units all together. Okay, so our first way of calculating area under a curve is to use the calculation of simply the area of a rectangle. And so we could do some things. Actually, this lesson starts us off with just asking how we could find an area of an odd shape like this. And so we could calculate that area by thinking, well, this is 1 wide. This height is 3, but here it's only 1. So we could, I don't know, we could make it into a triangle and a square, right? And we could add those two together. Or we could think about this like a half of a tall rectangle. If we kind of sketch that in, find that area of a full rectangle and split it in half. Either way, we're looking at something that would be an area of about roughly 2, I guess, for what this shaded area would represent. All right, coming up next at you is going to be how we're going to also use this when we don't have specific bars and how we can make a generalized rule that helps us calculate probability.